Tonight's journey begins with a thought that feels both enormous and strangely personal. It's about leaving home. Not just leaving a house or a city or even a planet, but leaving the entire solar system, the vast family of worlds and sunlight that has sheltered every human who has ever lived. It sounds dramatic when said that way, but there's also something quiet about it. After all, space doesn't roar or protest when something drifts away. It simply allows distance to grow. There's a common image in science fiction of spacecraft gliding effortlessly between stars, of people setting out and someday returning, like sailors crossing an ocean and eventually seeing familiar shores again. It's a comforting picture because it matches how travel works in our daily lives. You can leave home, go far away, and come back. A train departs and later returns. A plane crosses continents and lands again where it started. Even journeys that take years often circle back in the end. But space, as it turns out, doesn't always follow the same rules as oceans and skies. There's a quiet truth hidden in the physics of motion and energy, in the distances between stars and the fragile machinery we send beyond Earth. And that truth is this: leaving the solar system may not be a journey you can undo. It may be, in a very real sense, a one-way trip. We'll take our time with that idea. There's no need to rush toward conclusions. Like most things in the universe, the reasons unfold slowly, layer by layer, and each layer has its own story to tell. Before we go any farther, let me ask you something gentle and simple. Where are you listening from tonight? Maybe you're in a quiet apartment, or a house where the rest of the world has already gone to sleep. Perhaps you're listening through headphones, the outside sounds fading into the background. And what time is it for you right now? Late evening? Early morning? Somewhere in between? When clocks feel less important and thoughts drift a little more freely. It's interesting, isn't it? How the same moment can be experienced in so many different ways. Right now, somewhere on Earth, the sun is rising. Somewhere else, rain is tapping softly on a window. And somewhere far above, beyond the thin blue air, a handful of spacecraft are already on their slow journeys outward, moving farther from home with every passing second. If you find this kind of quiet exploration soothing, or simply a pleasant way to unwind at the end of the day, I'd be grateful if you considered liking the video or subscribing. It helps this calm little corner of science reach others who might be looking for the same gentle pause. But for now, there's nothing you need to do except listen, breathe, and let your mind wander at its own pace. Let's begin with something familiar. Imagine standing outside on a clear night. The sky stretches overhead, scattered with stars, and somewhere among them is a faint wandering light, perhaps Mars or Jupiter, drifting slowly against the background. It's easy, in moments like that, to feel that space is open and accessible, like a wide plain waiting to be crossed. After all, we've already sent machines to those planets. We've walked on the moon. We've photographed Saturn's rings and landed robots on comets. Step by step, it can seem as if the solar system is becoming smaller, more reachable, more like a map than a mystery. Yet distance in space has a peculiar way of hiding its true scale. Numbers that sound manageable, millions of kilometres, billions of kilometres, begin to lose meaning when there's nothing familiar to compare them to. A car crossing a continent feels like a long journey. A spacecraft crossing the orbit of Neptune travels distances so vast that even light, the fastest thing in the universe, needs hours to make the same trip. And beyond Neptune, beyond the outermost planets, the solar system doesn't simply stop. It stretches outward into regions so sparse and cold that sunlight itself becomes thin and faint. Objects drift there in slow, lonely orbits, remnants from the time when planets were still forming. And farther still lies a boundary that isn't really a line at all, but a gradual fading, where the influence of the sun weakens and the space between stars begins. To leave all of that behind is not like stepping outside a door. It's more like slipping free from an invisible current that has carried you your entire life. Gravity is part of that current. We feel it every day in the simple weight of our bodies, in the way objects fall, in the steady pull that keeps oceans in their basins and air wrapped gently around the planet. But gravity doesn't end at the edge of the atmosphere. It reaches outward, weakening with distance but never truly disappearing. The sun's gravity holds the planets in their paths, keeps comets returning, and guides even distant icy fragments in slow arcs that can last millions of years. To leave the solar system means to overcome that pull completely, to gain enough speed that the sun can never call you back. That might sound straightforward at first. Just go fast enough, you might think, and you'll escape. But speed in space isn't as simple as pressing an accelerator. Every increase in velocity demands energy, and energy in space is precious. Rockets must carry their fuel with them, and every kilogram of fuel adds weight that requires even more fuel to move. It's a delicate balance, like trying to lift yourself by standing in a bucket and pulling upward on the handle. This is one of the quiet reasons why journeys outward are easier than journeys back. When you depart from Earth, you can use the planet's motion, the gravity of other worlds, and carefully plan trajectories to gain speed. Space agencies have become remarkably skilled at this, sending spacecraft on winding paths that borrow energy from passing planets like a series of gentle pushes. But returning from the deep outer regions would require reversing that process, shedding enormous amounts of speed, carrying fuel across distances where there are no refueling stations, no convenient planets waiting to assist. The farther you go, the more difficult it becomes to come back, until the idea of return fades from practical planning altogether. You can see this in the history of space exploration. The Voyager spacecraft, launched in the 1970s, are still travelling outward today. They have crossed the region where the solar wind gives way to interstellar space. They carry golden records, messages intended for any distant intelligence that might one day find them. But there was never any intention of bringing them home. From the moment they left Earth, their journeys were understood to be one way. There's something quietly profound about that. These machines, built by human hands, are moving through darkness billions of kilometers away, never to return, carrying faint echoes of our voices and music into a future we'll never see. And yet, even Voyager is moving slowly by the standards of the cosmos. At its current speed, it would take tens of thousands of years to reach the nearest star if it happened to be heading in exactly the right direction, which it isn't. Space between stars is so vast that leaving the solar system is not the same as arriving anywhere. It's more like stepping off a shore into an ocean so wide that no opposite coast is visible and none may ever be reached. This raises a curious thought. When we speak about leaving the solar system, what does that really mean? Is there a boundary, a moment when you can look back and say, now we are outside? The answer is both yes and no. There are regions where the sun's influence weakens, where the solar wind fades, where interstellar particles begin to dominate. Scientists give these boundaries names: heliopause, termination shock, heliosphere, but in reality, they are gradual transitions, not walls or gates. A spacecraft crossing them doesn't feel a jolt or see a sign. The change is subtle, measured only by instruments and patient observation. And so leaving the solar system is not a single event but a process, a slow drifting away from warmth and light, from familiar gravitational patterns, from the steady presence of the sun in the sky. If you pause for a moment and imagine that journey, it has a certain stillness to it. The sun shrinking behind you, first a bright star, then a slightly brighter point among many. The planets gone, one by one, until only darkness and distant starlight remain. No sounds, no winds, no waves, just the quiet motion of a vessel coasting through an almost perfect vacuum. It's peaceful in a way, but also final, because the deeper you go, the harder it becomes to turn around. This isn't because of any rule or barrier placed by nature. It's simply the consequence of distance, energy, and time. The universe doesn't forbid return. It merely makes it so difficult that, for all practical purposes, it might as well. And that brings us gently to the heart of tonight's idea. Leaving the solar system is not impossible. We've already done it, in a sense, with small robotic explorers. But leaving in a way that allows a return, especially for something large, something carrying people, is another matter entirely. The physics of motion, the limits of propulsion, the immense scale of interstellar space, all of these conspire quietly, patiently, to turn departure into a one-way path. We'll explore those reasons together, one by one, moving slowly, letting each piece settle before adding the next. There's no need to rush ahead. Understanding comes more easily when it unfolds at a calm pace, like watching the night deepen outside a window. For now, just hold the image in your mind of a small spacecraft, far beyond the outer planets, moving steadily outward. No engines firing, no dramatic music, just inertia carrying it forward, kilometre by kilometre, year after year. Behind it, the sun grows dimmer. Ahead, the stars remain impossibly far. Why does the solar system feel so reachable to us in the first place, even though it is so vast? Why does it seem, in our imagination, like a neighbourhood we could wander through, rather than the immense gravitational domain it truly is? It's easy to forget just how large our surroundings really are, especially when every picture we see seems to place planets neatly side by side, lined up like ornaments on a shelf. Textbooks, posters, and even many documentaries compress the solar system into something that looks manageable, almost intimate. Mercury here, Venus there, Earth comfortably nearby, and beyond them the giant planets arranged in tidy sequence. The human mind naturally interprets such images as maps of a place that could be crossed with patience and determination, the way one might travel from one country to another. Yet those familiar diagrams are more like symbols than representations. If Earth were reduced to the size of a marble, the moon would not hover just a few centimetres away. It would be more than a metre distant, separated by an empty stretch of space larger than most people expect. And the next planet outward, Mars, would be many tens of metres away still. Jupiter would lie kilometres off in the distance, and Neptune, the outermost major planet, would be so far away that you might need to drive to reach it. What fills the vastness between these worlds is not a glowing haze or drifting clouds or anything that suggests connection. It is mostly emptiness, an emptiness so complete that a spacecraft travelling for months might pass nothing at all. No landmarks, no nearby objects, no sense of motion except the quiet reading of instruments. And still, despite this reality, the solar system feels close to us. It feels like a region that belongs to us, a place we have begun to explore and in a sense to understand. Part of that feeling comes from the steady rhythm of discovery over the past century. Each decade has brought new images, new missions, new evidence that human technology can reach farther than before. The moon once seemed unreachable, then became a place where footprints were left in dust that has not shifted since. Mars went from a distant red star to a landscape we can examine in detail, grain by grain, through the cameras of patient rovers. Step by step, this progress creates an impression of continuity, as though the path outward is simply a matter of continuing what we have already begun. If we can go to the moon, then Mars feels like the next step. If we can send probes to Jupiter and Saturn, then the outer edge of the solar system seems only a matter of time. But this sense of steady expansion can be misleading, because each step outward has required a disproportionately greater effort than the last. Travelling to the moon takes days, travelling to Mars takes months, reaching the outer planets requires years, and leaving the solar system entirely demands decades. The distances do not increase in a straight line. They grow enormously, stretching farther and farther apart until the scale becomes difficult to grasp in ordinary terms. Another reason the solar system feels reachable is that gravity, the force that binds it together, also helps us move within it. Spacecraft rarely fly in straight lines from one planet to another. Instead, they follow curved paths, guided by the gravitational pull of worlds along the way. This technique, often called a gravity assist, allows a spacecraft to gain speed without carrying extra fuel. By passing close to a planet, it can borrow a small portion of that planet's orbital energy, changing its trajectory and increasing its velocity. It's an elegant method, almost like stepping from one moving walkway to another, each giving you a gentle push forward. The Voyager missions used this approach beautifully, timing their launches so that the outer planets were aligned in a rare configuration. One by one, the spacecraft swung past Jupiter, Saturn, Uranus, and Neptune, each encounter adding speed and altering direction, sending them onward toward interstellar space. Hearing this, it's tempting to imagine the solar system as a series of stepping stones, a network of gravitational pathways that can carry travellers wherever they wish to go. And to some extent, that's true. Within the region of the planets, gravity can be used almost like a current, guiding motion and making journeys more efficient. Still, those pathways become fewer and weaker as you move outward. Beyond the major planets, there are no massive bodies to provide further assistance, only scattered remnants of ice and rock, objects too small to offer meaningful gravitational help. The helpful currents fade, leaving only the inertia of whatever speed you have already gained. That's one of the quiet turning points in any journey away from the Sun. Up to a certain distance, the solar system feels structured and navigable, a place with recognisable landmarks and useful gravitational aids. Past that point it becomes something else, a sparsely populated expanse where motion continues but guidance disappears. Familiarity also plays a powerful role in shaping our perception. Every planet in the solar system orbits the same star, shines in the same sunlight, and follows predictable paths that can be calculated centuries in advance. There's a comforting order to it all, a sense that this cosmic neighbourhood is stable and well understood. Even the asteroids and comets, which once seemed chaotic, now follow orbits that astronomers can track with remarkable precision. Living within such a predictable system gives rise to a subtle psychological effect. It feels safe, even when it's unimaginably large. The sun rises every day, the moon waxes and wanes, the planets return to familiar positions in the sky. Everything moves, but everything returns. Return is the key idea here, and it runs deep in human experience. Seasons return, migrating birds return, ships return to harbour. The expectation of return shapes how we think about journeys, making even long departures feel temporary. But the farther you go into space, the less that expectation holds true. Distances grow so vast and travel times so long that the concept of return begins to lose practical meaning. A spacecraft leaving the solar system at tens of kilometres per second is moving quickly by human standards, yet slowly by cosmic ones. At that speed, turning around and coming back would require enormous energy and decades, perhaps centuries of travel. Time itself becomes part of the equation. Human lives are measured in decades. Civilizations rise and change in centuries. But interstellar distances are measured in thousands or millions of years at current spacecraft speeds. A journey that lasts longer than a lifetime ceases to feel like a journey in the usual sense. It becomes something else, an irreversible passage. Another subtle factor that contributes to the illusion of reachability is the way communication works within the solar system. Signals travel at the speed of light, which is astonishingly fast, about 300,000 kilometers per second. On Earth, that speed makes communication feel instantaneous. Even with spacecraft near Mars, the delay is only a few minutes. Conversations aren't practical, but commands and responses can still be exchanged within a reasonable time. This creates the impression that even distant missions remain connected, still part of the same operational world. Engineers on Earth send instructions, spacecraft reply, data flows back, images appear, discoveries are announced. The sense of connection persists, reinforcing the idea that these distant places are still within reach. Yet as distances increase, even light begins to take longer and longer to cross them. Signals from the outer planets take hours to reach Earth. From the edge of the heliosphere, the region dominated by the sun's influence, the delay stretches to more than a day for a round trip. Communication slows, becoming less like conversation and more like sending messages in bottles across an ocean. Eventually, at interstellar distances, communication times would stretch into years. A message sent from a spacecraft halfway to the nearest star might not receive a reply within the lifetime of the people who sent it. At that point, connection becomes tenuous, almost symbolic. Our sense of reachability depends not only on distance, but on interaction. When interaction fades, so does the feeling that a place is truly part of our world. There is also the matter of scale in time as well as space. The solar system is about 4.6 billion years old, and its structure changes slowly, on timescales far longer than human history. Planets move in their orbits with patient regularity. The sun shines steadily, changing only gradually over millions of years. To us, this stability feels permanent, as though the solar system were a fixed stage on which our lives unfold. But permanence can be deceptive. The sun itself is moving through the galaxy, carrying all its planets along in a vast orbit around the Milky Way. At this moment, we're travelling through space at hundreds of kilometres per second, even as we sit still on the surface of Earth. The stars we see in the night sky are not fixed either. They drift slowly, changing positions over centuries and millennia. In that sense, the solar system is not a stationary home, but a moving one, a kind of cosmic ship sailing through a larger ocean of stars. Leaving it behind is not merely a matter of crossing a boundary. It is stepping off a moving vessel into a sea that stretches in all directions. Considering this, the illusion of reachability begins to fade, replaced by a clearer understanding of what departure truly means. It means not only overcoming the sun's gravity, but also accepting that the place you left will continue moving, carrying with it everything familiar, while you drift on a different path through the galaxy. There's something quietly profound about that realization. Home, in the cosmic sense, is not just a location, but a shared motion, a common journey through space and time. To leave it is to separate from that shared path, to follow a trajectory that diverges more and more with each passing year. And yet, despite all these realities, the solar system will probably continue to feel reachable to us for a long time. Human imagination is resilient, and our history is filled with examples of journeys that once seemed impossible. Oceans were once barriers beyond which maps showed only blank spaces. Mountains were once thought impassable. The sky itself was once considered unreachable. Each time a boundary was crossed, the world seemed to shrink, and the next boundary appeared less intimidating. It's natural then to assume that the same pattern will continue indefinitely, that technology will always find a way, that distances will yield as they have before. But physics does not always yield to determination. Some limits are not merely technological but fundamental, rooted in the relationships between energy, mass, and distance. The farther one travels from the sun, the more those limits assert themselves, quietly but firmly. To understand why leaving the solar system is so difficult, it helps to pause for a moment and think about something that is always present, always acting, and yet almost never noticed. Gravity doesn't make a sound, it doesn't glow or shimmer, it doesn't announce itself in any obvious way, and yet it is constantly at work shaping the motion of planets, guiding comets, and holding entire systems together with a quiet persistence that never fades. Here on Earth, gravity feels ordinary. It's the reason your feet rest on the floor, the reason a cup stays on a table instead of drifting away, the reason rain falls downward rather than sideways or upward. Because we experience it every moment of our lives, it becomes almost invisible in our awareness, like the steady pressure of air or the gentle pull of the ground beneath us. But gravity is not only a local force, it reaches outward, weakening with distance but never truly disappearing. The Earth holds the Moon in its orbit, even though the Moon is hundreds of thousands of kilometers away. The Sun, far more massive than any planet, extends its influence across billions of kilometers, binding the entire solar system into a single slow-moving dance. Every planet, every asteroid, every comet you have ever seen in a photograph is moving under the Sun's gravitational pull. Even objects so distant that sunlight barely touches them still feel that attraction, still follow paths shaped by it. Gravity, in that sense, is less like a rope pulling objects inward and more like a deep valley in the landscape of space itself. Everything tends to move along the slopes of that valley unless something gives it enough energy to climb out. That image of a valley can be helpful. Imagine placing a marble in a shallow bowl. The marble rolls back and forth, gradually settling at the lowest point. To remove it, you must give it enough energy to push it up the side and over the rim. If you don't push hard enough, it will roll partway up and then fall back again, returning to the centre. Leaving the solar system is, in a sense, like pushing a marble out of an enormous invisible bowl. The sun's gravity forms the bowl, and everything within it moves along paths determined by how much energy it has. Planets like Earth and Mars are not sitting still. They're constantly moving sideways at high speed, falling toward the sun but missing it, tracing out orbits that repeat year after year. This sideways motion is important, because it shows that gravity doesn't simply pull things straight inward. Motion and gravity combine to create orbits, stable paths that can last for billions of years. But an orbit is still a kind of captivity, even if it is a graceful one. The object remains bound to the gravitational well, circling endlessly unless something changes its energy. For a spacecraft to leave the solar system, it must gain enough energy to escape that well entirely, not just to reach a high point and fall back, but to climb over the rim and continue outward forever, never turning around unless it expends energy to do so. This required speed is known as escape velocity, but the name can be a little misleading. It doesn't mean a sudden burst of speed that instantly frees you. Instead, it means reaching a velocity that ensures gravity can never slow you to a stop and pull you back. From Earth's surface, escape velocity is about 11 kilometers per second, far faster than any aircraft can travel. Rockets must reach this speed to break free from Earth's gravitational pull. But escaping Earth is only the first step. The Sun's gravity is far stronger on the scale of the solar system, and escaping it requires far more energy. Earth itself is already moving around the Sun at about 30 kilometers per second. That motion helps spacecraft, because when they depart Earth in the right direction, they inherit some of that speed. It's like running forward on a moving walkway instead of standing still. The motion of Earth provides a head start. Even with that advantage, leaving the Sun's gravitational influence requires tremendous energy. Spacecraft like Voyager achieved it not by carrying vast quantities of fuel, which would have been impractical, but by carefully using the gravity of giant planets to gain speed. Each close approach acted like a slingshot, redirecting the spacecraft and increasing its velocity relative to the Sun. This technique works because planets themselves are moving. When a spacecraft passes behind a planet in its orbit, it can steal a tiny fraction of that planet's momentum, gaining speed while the planet loses an imperceptible amount. The exchange is so small that it has no noticeable effect on the planet, but for a lightweight spacecraft, it can make the difference between remaining bound and escaping entirely. Even so, the speeds involved are modest by cosmic standards. Voyager 1, one of the fastest human-made objects ever launched, travels at about 17 kilometers per second relative to the Sun. That sounds fast, and it is by everyday measures, but at that speed, it would take more than 70,000 years to reach the nearest star if it were headed in that direction. Gravity's invisible grip is not a wall that must be broken through in a single moment. It is more like a long, gradual slowing. As a spacecraft moves outward, the Sun's gravity continues to pull on it, reducing its speed little by little. If the spacecraft has not reached escape velocity, that slowing will eventually bring it to a stop, after which it will begin to fall back inward, tracing a long, slow arc toward the Sun. Only if its initial speed is high enough will it continue outward indefinitely, its velocity decreasing but never reaching zero. Even then, the Sun's gravity never truly stops acting. The spacecraft remains influenced, its path subtly curved, its speed still changing, though more and more slowly as distance increases. This is an important point, because it reveals something about gravity that is easy to overlook. Gravity does not have a sharp boundary. There is no line you cross where the Sun's pull suddenly disappears. Instead, the influence fades gradually, extending outward forever, though becoming weaker and weaker with distance. That means leaving the solar system is not like stepping outside a door. It is more like walking away from a campfire on a cold night. The warmth fades slowly. The light grows dimmer. Long after the fire is out of sight, a faint glow may still be visible, and the warmth may still be just barely felt. In the same way, a spacecraft travelling far beyond the planets is still, in a subtle sense, within the Sun's reach. The gravitational influence is tiny, but it never entirely vanishes. Another aspect of gravity makes return journeys especially difficult. To leave the solar system, a spacecraft needs enough energy to escape the Sun's pull. But to come back, it would need to shed that energy again, slowing itself enough to fall inward rather than continuing outward. Slowing down in space is not easy. On Earth, friction with air and contact with the ground naturally reduce motion. A car slows when you release the accelerator because of air resistance and rolling friction. But in the near-perfect vacuum of space, there is nothing to slow you unless you actively fire engines in the opposite direction. That means any spacecraft hoping to return would need to carry enormous amounts of fuel to decelerate, fuel that would also need to be accelerated during departure, increasing the energy required at every stage. The farther you travel, the more energy you must remove to come back, and the more impractical the journey becomes. Gravity, in this sense, acts like a kind of one-way slope. Going downhill, gaining speed with the help of planetary gravity and the motion of Earth, is relatively efficient. Climbing back uphill, against the pull of the Sun, and without the benefit of atmospheric braking or nearby massive bodies, is vastly more demanding. There is also a quieter effect at work, one that becomes significant over very long distances. The solar system itself is moving through the galaxy, orbiting the centre of the Milky Way at hundreds of kilometres per second. This spacecraft leaving the solar system is not leaving a stationary point, but a moving one, and matching that motion again after travelling far away would require precise navigation and additional energy. Over decades and centuries, even small differences in velocity and direction can lead to enormous separations. A spacecraft drifting through interstellar space would gradually find that the solar system is no longer where it once was relative to the background of stars. Returning would not simply mean turning around, it would mean calculating and matching a moving target across vast distances. All of this makes gravity's role in shaping journeys both subtle and profound. It is not merely a force that holds planets in place. It is a sculptor of paths, a silent guide that determines what is easy, what is difficult, and what may be practically impossible. And yet, gravity is also what makes the solar system feel like home. The same force that makes departure so difficult is the one that keeps Earth in a stable orbit, maintaining the conditions that allow oceans to remain liquid, climates to persist, and life to flourish. Without the sun's gravitational hold, Earth would drift into the darkness, a frozen world wandering between stars. There is a certain symmetry in that idea. The force that nurtures life here also makes leaving permanently one of the most demanding journeys imaginable. If you imagine again that small spacecraft drifting outward, year after year, you can picture gravity at work in a quiet way. No visible tether connects it to the sun, yet its motion is still shaped by that distant star. Its speed decreases slowly, almost imperceptibly, as it climbs higher and higher out of the gravitational well. Eventually it reaches a point where the sun's pull becomes so faint that other influences begin to matter more. The gravity of passing stars, the gentle tides of the galaxy itself. At that distance, the solar system is no longer the dominant force shaping its path. But reaching that point takes decades, and by the time it does, the spacecraft is so far away and moving so fast relative to the inner planets that returning would demand an extraordinary expenditure of energy and time. This is why missions that leave the solar system are designed with no expectation of return. Engineers and scientists plan them as outward journeys from the very beginning, knowing that gravity's invisible grip, once overcome, becomes a barrier in the opposite direction. And so gravity, quiet and unseen, plays a central role in turning departure into a one-way path. It shapes the energy required to leave, the difficulty of slowing down, and the immense scales of time involved in any attempt to reverse course. Speed, in everyday life, feels straightforward. You press a little harder on a car's accelerator, and the scenery begins to pass more quickly. A train moves faster than a bicycle, an airplane faster than a train, and the differences, though impressive, still exist within a range that the human mind can grasp. Even the fastest aircraft cross continents in hours, and the distances involved remain tied to familiar experiences of travel and geography. Space, however, changes the meaning of speed in ways that are not immediately obvious. The distances are so vast, and the forces involved so subtle yet persistent, that reaching a certain velocity is not just a matter of arriving sooner. It determines whether you arrive at all, whether you remain bound to a gravitational system, or whether you slip free of it forever. This is where the idea of escape velocity becomes essential. It is one of those concepts that sounds technical at first, but turns out to describe something quite intuitive. Escape velocity is simply the speed an object must reach to overcome the gravitational pull of another body without needing further propulsion. If you reach that speed, gravity will never bring you back, even though it continues to act on you, slowing you gradually as you move farther away. To picture this, it can help to imagine throwing a ball straight upward. If you toss it gently, it rises a short distance and falls back into your hand. Throw it harder, and it climbs higher before returning. Throw it harder still, and it rises higher again. But no matter how strong your throw, the ball eventually stops and falls back, because Earth's gravity slows it down until its upward motion ends. Now imagine a throw so powerful that the ball never stops rising, never reverses direction, never falls back. That would mean it had reached escape velocity. It would continue moving away from Earth forever, slowing all the while but never quite coming to a halt. For Earth, that speed is about 11 kilometers per second, roughly 40,000 kilometers per hour. Rockets launching from Earth must reach at least this speed, or they will remain gravitationally bound and eventually fall back. Yet escaping Earth is only the first step. Earth itself orbits the Sun, and even after a spacecraft leaves Earth's gravity behind, it is still deep within the Sun's gravitational well. To leave the solar system entirely requires reaching escape velocity from the Sun, which is much higher when measured from Earth's orbit. Fortunately, spacecraft already possess a portion of this velocity simply by sharing Earth's motion. Earth travels around the Sun at about 30 kilometers per second, and anything launched from Earth carries that motion along with it. This means a spacecraft does not need to generate all the necessary speed on its own. It begins its journey already moving swiftly through space. Even though that motion is not noticeable to us on the surface, still, achieving solar escape velocity demands careful planning and enormous energy. Rockets provide the initial boost, but beyond that, gravity assists from planets often play a decisive role. Without them, the amount of fuel required would be impractically large. What makes escape velocity so significant is not just the number itself, but what it represents. Crossing that threshold changes the nature of the journey. Below escape velocity, motion is temporary in a certain sense. An object may travel far, but gravity ensures that its path eventually curves back inward. Above escape velocity, the path becomes open-ended. The object is no longer confined to an orbit that returns it to its starting region. In practical terms, this means that once a spacecraft has escaped the Sun's gravitational hold, returning becomes vastly more difficult. To come back, it must shed enough energy to fall inward again, essentially reversing the conditions that allowed it to escape in the first place. This reversal is far harder than the departure. Rockets are efficient at accelerating objects, but decelerating them in deep space requires carrying fuel for engines that must fire in the opposite direction, and that fuel must itself be accelerated at the start of the journey. Each kilogram added for the return trip increases the energy required to leave, which in turn demands more fuel and so on. The requirements grow rapidly, making round-trip journeys across such distances extraordinarily demanding. There is another aspect of escape velocity that is easy to overlook. It is not a wall you pass through at a specific moment. There is no sudden change, no invisible line marking the transition from bound to unbound motion. Instead, escape velocity describes a condition of energy. If your total energy relative to the gravitational body is positive, you will escape. If it is negative, you will remain bound. That distinction may sound abstract, but it has real consequences. A spacecraft travelling just below escape velocity might take years or even centuries to fall back inward, tracing a long, stretched-out orbit that carries it far from the Sun before turning around. To an observer watching over a short period, it might appear to be escaping, even though gravity will eventually bring it back. Only by exceeding escape velocity can it truly depart forever. It's interesting to consider how delicate this balance can be. A difference of a few meters per second in velocity, tiny compared to the overall speed of tens of kilometers per second, can determine whether a trajectory is bound or unbound. Navigators planning interplanetary missions must account for these differences with extraordinary precision, calculating trajectories that unfold over decades. Once a spacecraft is on an escape trajectory, its speed relative to the Sun gradually decreases as gravity pulls against it. But because its initial velocity was high enough, it never quite slows to zero. Instead, it approaches a steady outward speed, coasting through interstellar space long after its engines have fallen silent. This coasting motion is another feature of space travel that can feel counterintuitive. On Earth, motion requires constant effort. A bicycle slows if you stop pedaling, and a car slows if you release the accelerator. But in space, with almost no friction, motion continues indefinitely. A spacecraft that reaches escape velocity and turns off its engines will keep moving outward, year after year, century after century, carried forward by inertia alone. That silent persistence is one reason escape velocity changes everything. Once achieved, it sets the stage for journeys that extend far beyond any human lifetime. The spacecraft becomes, in a sense, a messenger sent into the future, continuing its path long after those who launched it are gone. Yet escape velocity also reveals something humbling about our technological limits. Chemical rockets, the kind used for most space missions, have practical limits on how much speed they can provide. Each kilogram of fuel produces only a certain amount of thrust, and increasing fuel mass quickly leads to diminishing returns. This is why gravity assists are so valuable, and why missions leaving the solar system are relatively rare. Even with advanced propulsion concepts, the energies required for fast interstellar travel remain enormous. Reaching escape velocity from the Sun is one challenge. Reaching speeds that would allow travel to nearby stars within a human lifetime is another entirely, requiring velocities many times greater. For now, our spacecraft leave the solar system slowly, taking decades to cross its outer boundaries and thousands of years to approach even the nearest stars. They are not fast travellers in cosmic terms, but they are persistent ones, moving steadily outward, never turning back. There is a quiet inevitability in that motion. Once escape velocity has been reached, and the engines have long since fallen silent, the journey becomes irreversible in any practical sense. The energy required to stop, turn and return would be far greater than what was needed to depart, and no spacecraft built so far carries the means to do it. It's worth reflecting on how different this is from most journeys in human history. A ship crossing an ocean may be carried by winds and currents, but it can always turn around, catch a different wind and return. An airplane can land, refuel and depart again. Even explorers travelling across deserts or mountains usually retain the option of retracing their steps. But a spacecraft that has reached escape velocity and travelled far beyond the planets has no such easy option. It cannot refuel in interstellar space. It cannot rely on atmospheric drag to slow down. It cannot anchor itself to anything solid. It is committed to its path in a way that feels almost philosophical, as though the laws of motion themselves have sealed its course. This commitment is not dramatic or sudden. It happens quietly, in the mathematics of trajectories and the measured firing of engines, in the precise alignment of planets and the careful timing of maneuvers. But once it happens, it is final. And so, escape velocity is more than a number. It is a threshold that separates two kinds of motion, two kinds of journeys. On one side lies the realm of orbits, of return and repetition, of paths that circle back. On the other lies the open road of interstellar space, where paths do not close and return is no longer part of the plan. If you imagine again that small spacecraft drifting outward, now far beyond the outer planets, its speed slowly decreasing but never reaching zero, you can sense how escape velocity shapes its fate. The sun grows dimmer behind it, the stars ahead remain distant, and the path it follows stretches onward without end. At first glance, rockets seem almost magical. A column of fire erupts beneath a machine made of metal and electronics, and something heavier than any aircraft ever built rises into the sky, climbing steadily until it disappears into the darkness above the atmosphere. The spectacle is so dramatic that it's easy to imagine rockets as powerful beyond measure, engines capable of pushing anything anywhere if only we built them large enough. But rockets are not magical at all. They are bound very strictly by the laws of physics, and those laws impose limits that become more severe the farther you try to travel. The deeper one looks into how rockets actually work, the clearer it becomes that there is a practical boundary to what they can accomplish, especially when the journey involves leaving the solar system and returning again. The principle behind a rocket is simple. To move forward, it throws mass backward. Fuel burns in a combustion chamber, producing hot gas that expands rapidly and escapes through a nozzle. As the gas rushes out, the rocket is pushed in the opposite direction. This is Newton's third law in action. For every action, an equal and opposite reaction. That principle works beautifully, but it comes with an unavoidable consequence. A rocket must carry the mass it intends to throw backward. The fuel that provides thrust also adds weight, and that weight must itself be lifted and accelerated. This creates a problem that engineers call the tyranny of the rocket equation, a phrase that sounds dramatic but reflects a very real constraint. The rocket equation describes how much fuel is required to achieve a certain change in velocity, often called delta V. The relationship is not linear. Doubling the required velocity does not merely double the fuel requirement, it increases it exponentially. Each additional increment of speed demands disproportionately more fuel, and that fuel increases the mass of the rocket. which in turn requires even more fuel to accelerate. It becomes a cycle that quickly runs into practical limits. There comes a point where adding more fuel no longer helps, because the fuel needed to lift that additional fuel becomes overwhelming. Engineers can improve efficiency, reduce structural weight, and design better engines, but the fundamental relationship remains. This is why rockets are built in stages. When a rocket launches, large booster stages burn their fuel and then detach, falling away so that the remaining vehicle is lighter. By shedding empty tanks and engines, the rocket avoids carrying unnecessary mass into space. Staging is one of the key techniques that makes spaceflight possible at all. Even so, reaching orbit around Earth requires enormous effort. A typical launch vehicle is mostly fueled by mass, often more than 90%. The actual payload, the spacecraft or satellites at the top, represents only a tiny fraction of the total weight at liftoff, and orbit is only the beginning. To leave Earth's gravity entirely requires additional speed. To escape the Sun's gravity requires still more. Each step outward demands more energy, more fuel, and more careful planning. There is also a limit to how efficient chemical rockets can be. The energy released by burning fuel depends on chemical reactions, and those reactions can only release a certain amount of energy per unit mass. Engineers can optimize fuels, improve combustion, and design better nozzles, but they cannot exceed the fundamental limits set by chemistry. More advanced propulsion systems, such as ion engines, offer greater efficiency by accelerating small amounts of propellant to extremely high speeds. These engines can operate for months or years, gradually building up velocity. They are excellent for deep space missions where patience is possible, but they produce very low thrust and cannot lift heavy payloads from Earth's surface. Even nuclear propulsion concepts, which could provide higher efficiency than chemical rockets, face enormous engineering and safety challenges. And while such technologies may one day expand our capabilities, they do not eliminate the basic problem. Accelerating mass to high speeds requires vast amounts of energy, and carrying that energy with you adds weight that must itself be accelerated. When considering a journey out of the solar system and back again, these constraints become especially severe. A spacecraft leaving Earth must carry enough fuel not only to escape Earth's gravity, but also to maneuver through the solar system, adjust its trajectory, and, if return is intended, slow down and reverse course. Slowing down in space is just as demanding as speeding up. Every meter per second of velocity that must be cancelled requires fuel burned in the opposite direction. A spacecraft returning from interstellar space would need to shed tens of kilometers per second of speed, a task requiring enormous amounts of propellant. And unlike journeys within the inner solar system, there are no convenient places to refuel. On Earth, vehicles can stop at stations, replenish fuel, and continue. Aircraft land at airports, ships dock at ports, and even long-distance trains take on supplies along the way. In deep space, there are no stations, no depots, no infrastructure of any kind. A spacecraft must carry everything it needs from the moment it departs. Every kilogram of fuel must be lifted from Earth's gravity well, accelerated into space, and carried for years or decades. This requirement grows rapidly with distance. A mission to Mars already involves careful calculations to minimize fuel consumption, often relying on planetary alignment to reduce the energy needed. Missions to the outer planets take advantage of gravity assists, borrowing momentum from massive worlds to reduce fuel requirements. But once a spacecraft leaves the region of the planets, those opportunities vanish. There are no large bodies to provide gravitational boosts, no nearby sources of materials, and no atmosphere to use for braking. The spacecraft becomes entirely dependent on whatever fuel and systems it carried from the beginning. This is one of the quiet reasons why the first missions to leave the solar system were designed as one-way journeys. Engineers knew that carrying enough fuel to return would make the spacecraft far heavier, requiring larger rockets to launch them, which in turn would require more fuel still. The requirements would spiral upward until the mission became impractical. Another limitation comes from the reliability of machinery over long periods. Rockets and spacecraft are complex systems with many components that must function correctly. Even with careful design and redundancy, parts wear out, electronics degrade, and materials age under exposure to radiation and extreme temperatures. A journey lasting decades places extraordinary demands on every component. Planning a return trip that might require centuries would mean designing systems capable of operating far longer than any current technology has demonstrated. The longer the journey, the more likely it becomes that something will fail, and in the emptiness of deep space there is no repair facility, no rescue mission waiting nearby. Energy for onboard systems is another constraint. Spacecraft travelling far from the sun cannot rely on solar panels because sunlight becomes too weak. Instead, they use radioisotope thermoelectric generators, devices that convert heat from the decay of radioactive materials into electricity. These power sources are reliable, but limited. Their output declines slowly over time, and eventually there is not enough energy to operate instruments or transmit signals. This gradual fading of power has already been observed in spacecraft like Voyager. Instruments have been turned off one by one to conserve energy, extending the mission as long as possible. Even so, the time will come when communication ends, not because the spacecraft has stopped moving, but because it no longer has the power to speak. All of these limits, fuel, propulsion efficiency, reliability, and energy supply, combine to shape what rockets can realistically achieve. They do not prevent us from exploring the solar system, but they make certain kinds of journeys far more difficult than they might appear in stories or films. It is sometimes tempting to imagine that future technology will remove these limits entirely, allowing spacecraft to travel freely between stars as ships cross oceans. And it is true that new propulsion methods may one day make interstellar travel more practical. Concepts involving fusion propulsion, antimatter, or light sails are being studied, each offering the possibility of higher speeds and greater efficiency. Yet even these advanced ideas face challenges rooted in fundamental physics. Energy must still be generated, stored, and directed. Heat must still be managed. Structures must still withstand the stresses of acceleration and the hazards of interstellar space. There is no indication that travel between stars will ever be easy, and return journeys will likely remain far more demanding than departures. For now, rockets remain our primary means of reaching space, and their limits are real and measurable. They can send probes to distant worlds, place telescopes in orbit, and even carry humans to the moon, but they cannot yet support round trips beyond the outer solar system. This does not diminish their achievements. On the contrary, it highlights how remarkable it is that we have reached as far as we have. Every mission to the outer planets, every spacecraft that has crossed the Heliopause, represents an extraordinary triumph of engineering and patience. Still, the limits remain, quiet and persistent, shaping every plan and every trajectory. They are part of the reason why leaving the solar system is, in practical terms, a one-way journey. The fuel required to come back is simply too great, the energy demands too high, and the infrastructure needed to support such travel does not yet exist. And so, spacecraft continue to depart, carrying instruments and messages into the darkness, knowing from the moment of launch that they will never return. Their paths are set by the fire of their engines and the gravity of the worlds they pass, and once they move beyond the reach of those worlds, they travel onward alone. There is a quiet assumption that slips into the mind whenever we picture the solar system. We imagine it as something stable and centred, the sun fixed in place, the planets circling in orderly paths, everything contained within a kind of cosmic snow globe. In diagrams, the sun sits calmly at the centre, and the orbits form neat rings around it, as though the entire system were resting peacefully in a still universe. But the truth is far more dynamic, and in its own way, far more humbling. The sun is not standing still. Neither is Earth, nor any of the planets, nor the distant comets drifting at the edge of the solar system. Everything here is in motion, travelling together through space at speeds that are difficult to imagine, carrying us along whether we notice it or not. Right now, at this very moment, you and I are moving through the galaxy at roughly 220 kilometers per second. That is the speed at which the solar system orbits the centre of the Milky Way. It's a journey that takes about 230 million years to complete a single circuit, a span of time so long that when the dinosaurs last walked the Earth, the solar system was in an entirely different region of the galaxy. This motion is smooth and continuous, and because everything around us shares it, we don't feel it at all. There is no rushing wind, no vibration, no sensation of movement. Just as passengers on a smoothly flying airplane can forget they are travelling hundreds of kilometres per hour, we forget that our entire world is part of a much larger voyage. Yet this motion has profound implications for what it means to leave the solar system. To understand why, it helps to picture the solar system not as a stationary set of orbits, but as a kind of moving bubble drifting through the galaxy. The sun's gravity holds the planets in their paths, but the entire structure is also travelling, carried along by the gravitational pull of billions of stars in the Milky Way. If you were able to watch the solar system from far outside, over millions of years, the paths of the planets would not look like simple circles around a fixed point. Instead, they would trace spirals, looping forward as the sun moves onward through space. Earth does not circle a stationary sun. It circles a sun that is itself in motion, and so our path through the galaxy is a kind of winding thread, never repeating, never returning to exactly the same place. This realization changes the meaning of departure. Leaving the solar system is not like stepping off a dock onto still water. It is more like stepping off a moving ship into an ocean that is itself in motion. The place you left behind is not waiting for you at a fixed location. It is continuing onward, carried along by forces far larger than anything in the solar system itself. Consider what this means over long periods of time. A spacecraft that leaves the solar system and travels outward for decades will not simply find the sun behind it in the same position relative to the stars. The sun, along with all its planets, will have moved significantly along its galactic orbit. Returning would require not only reversing direction, but also matching the changing position and velocity of a destination that has been travelling through space the entire time. The difficulty of that task grows with every passing year. There's also another motion to consider, one that is quieter but equally important. The sun is not only orbiting the centre of the galaxy, it is also drifting relative to nearby stars. The stellar neighbourhood is not static. Stars move in their own orbits, each following a path shaped by the galaxy's gravitational field. Over tens of thousands of years, the constellations themselves slowly change, their familiar patterns gradually shifting as stars drift in different directions. If you could watch the night sky over 100,000 years, the shapes of Orion, Ursa Major, and the rest would slowly distort, like figures drawn on a flexible surface that is being gently stretched and reshaped. The sky of the distant future will not look exactly like the sky we know today. This constant motion means that the solar system's position relative to other stars is always changing. A spacecraft leaving today is not simply travelling through a static environment, it is moving through a region of space where everything else is in motion as well. There is a quiet beauty in that thought. Space is not a frozen stage, but a flowing environment, a vast choreography of stars and planets, each following its own path, sometimes drawing closer, sometimes drifting farther apart. But there is also a practical consequence. Navigation across interstellar distances becomes far more complex when both the traveller and the destination are moving. Imagine trying to throw a ball to someone who is running across a field. You cannot aim at where they are now. You must aim at where they will be when the ball arrives. The farther the distance and the longer the travel time, the more difficult this prediction becomes. On the scale of interstellar travel, these challenges multiply enormously. A spacecraft travelling for centuries would need to account for the changing positions of stars, the motion of the solar system, and the gravitational influences of objects it has not yet encountered. Returning to the solar system would not be a matter of simply turning around and heading back along the same path. That path would no longer lead to where the solar system had been. It would lead to empty space, to a region the sun had passed through long ago. To find home again, a spacecraft would need to calculate and match the solar system's new position and velocity, adjusting its trajectory over vast distances with extraordinary precision. And all of this would require energy, fuel, and functioning systems over timescales far longer than any spacecraft has ever operated. There is another subtle effect of motion that becomes important at large distances. The galaxy itself exerts gravitational forces not strong enough to dominate within the solar system, but significant over interstellar scales. A spacecraft travelling far from the sun gradually becomes more influenced by the gravitational field of the Milky Way as a whole, as well as by the occasional passing star or molecular cloud. These influences are gentle but persistent. Over decades and centuries they can alter a trajectory slightly, nudging a spacecraft in ways that are difficult to predict perfectly. The farther one travels, the more these small effects accumulate, and the more challenging it becomes to retrace a precise path back to the starting point. All of this contributes to the quiet truth that leaving the solar system is not just about overcoming gravity or achieving escape velocity. It is about departing from a moving system into an environment where motion is the rule rather than the exception. And there is something else to consider, something that is easy to overlook because it unfolds so slowly. The sun itself is not eternal in its present form. Over billions of years it will change, growing brighter, eventually expanding into a red giant long after humanity, in its current form, is gone. The solar system we know today is only a temporary arrangement in a much longer story. That doesn't affect the practicalities of missions lasting decades or centuries, but it does remind us that even the most stable structures in the universe are part of ongoing change. Nothing stands still forever, not even stars. Reflecting on this can shift the way we think about journeys. On Earth, returning home usually means returning to a place that is much the same as when you left it. A house remains where it was built. A city grows and changes but stays rooted in the same landscape. Even continents drift so slowly that their motion is imperceptible within a lifetime. In space, the scales are different. Home is not anchored to a fixed point. It is part of a system in motion, and the longer you're away, the farther that system travels. There is a gentle irony in this. The solar system feels like a stable refuge, a place of predictable orbits and familiar rhythms. Yet on the scale of the galaxy, it is a traveller, carrying us through space on a journey that began billions of years ago and will continue long after we're gone. When a spacecraft leaves the solar system, it is not merely leaving a place. It is parting ways with a shared trajectory, stepping off a moving platform into a vast and shifting environment. That separation grows with time. Each year, each decade, the distance between the departing spacecraft and the solar system increases, not only because of the spacecraft's motion, but also because of the sun's motion through the galaxy. Eventually, the separation becomes so great, and the differences in velocity so significant, that returning would require an extraordinary expenditure of energy and an extraordinary level of precision, far beyond what current technology can achieve. And so the motion of the solar system itself becomes another quiet reason why leaving is a one-way trip. It is not a barrier in the sense of a wall or a boundary. It is a gradual divergence, a growing separation in space and time that makes return less and less practical with every passing year. If you were to ask where the solar system ends, the first answer that might come to mind would be simple. It ends at the orbit of the last planet. Neptune circles the Sun at an immense distance, far beyond the warmth that sustains life on Earth, and for many years it was natural to think of that distant orbit as the outer boundary of our celestial neighbourhood. Beyond Neptune surely must lie the true beginning of interstellar space. But that tidy picture, like many tidy pictures in astronomy, turns out to be incomplete. The solar system does not end at Neptune, or even at Pluto, or at any single clearly marked boundary. Instead, it fades gradually, its influence stretching outward into regions so vast and sparse that the transition from home to elsewhere becomes almost impossible to pinpoint. To understand why, it helps to think about what defines the solar system in the first place. Is it the region where the sun's gravity dominates? Is it the region filled with objects that orbit the sun? Or is it the region shaped by the solar wind, that steady stream of charged particles flowing outward from the sun in all directions? Each of these definitions leads to a different boundary, and none of them lies anywhere near the orbit of the outer planets. Let's begin with the solar wind, because it forms one of the most intriguing frontiers. The sun is not just a glowing sphere of light, it is also a continuous source of energetic particles. These particles stream outward at hundreds of kilometers per second, carrying with them the sun's magnetic field and forming a vast bubble in space known as the heliosphere. Inside this bubble, the solar wind dominates the environment. It pushes outward against the thin gas and magnetic fields that fill the space between stars, creating a region where conditions are shaped more by the sun than by the galaxy beyond. Earth, the planets, and all the spacecraft we have ever launched exist within this immense invisible bubble. For a long time, the heliosphere was only a theoretical concept, something scientists inferred from indirect measurements and models. But in recent years, spacecraft like Voyager 1 and Voyager 2 have actually crossed its outer boundary, a region known as the Heliopause. There, the influence of the solar wind weakens, and the environment begins to resemble the interstellar medium more than the space within the solar system. This crossing was not dramatic. There was no visible line, no sudden change in scenery. The spacecraft simply detected a shift in particle densities and magnetic fields, subtle clues that they had entered a new region of space. It was less like crossing a border and more like walking from one climate into another, where the air feels slightly different, but the landscape remains much the same. Even so, crossing the heliopause does not mean leaving the solar system in a gravitational sense. The Sun's gravity extends far beyond the heliosphere, reaching distances measured not in billions but in trillions of kilometres. Objects far outside the heliopause can still be bound to the Sun, following orbits that take millions of years to complete. One of the regions where this becomes most apparent is the Kuiper belt, a vast collection of icy bodies that begins beyond Neptune's orbit and extends outward for billions of kilometres. Pluto is part of this region, but it is only one of many objects, most of them small, dark and distant, circling the Sun in slow, elongated paths. The Kuiper belt is not densely populated. The distances between objects are enormous, and a spacecraft passing through it might travel for days or weeks without coming anywhere near another body. Yet it is still unmistakably part of the solar system, a reservoir of material left over from the time when the planets were forming. Beyond the Kuiper belt lies an even more mysterious region, one that stretches so far that it is difficult to imagine in concrete terms. This is the domain of the Oort cloud, a vast spherical halo of icy fragments that may extend tens of thousands of astronomical units from the Sun. An astronomical unit, the average distance from Earth to the Sun, is about 150 million kilometres, so the scale of the Oort cloud is almost beyond comprehension. If the Earth's orbit were the size of a coin, the outer edge of the Oort cloud might lie hundreds of metres away. And yet even there, at those immense distances, objects are still bound to the Sun by gravity, tracing orbits that can take millions of years to complete. This means that the gravitational boundary of the solar system lies far beyond the regions we have explored directly. Voyager 1, the most distant spacecraft ever launched, has travelled more than 160 astronomical units from the Sun, a staggering distance by human standards. And yet, it has barely begun to approach the inner edge of the Oort cloud, let alone its outer limits. In a very real sense, we are still deep within the solar system, even as our most distant probes drift through interstellar space. There is something quietly astonishing about that realization. The solar system is not merely a collection of planets, but a vast gravitational domain extending trillions of kilometers in every direction. It is less like a city and more like a continent, its edges fading into the surrounding ocean in ways that are difficult to define precisely. This gradual fading has practical consequences for any journey outward. A spacecraft leaving the solar system does not simply cross a boundary and enter a completely different environment. Instead, it passes through layers, each one slightly less influenced by the Sun than the last. The solar wind weakens, the density of interplanetary dust decreases, the number of orbiting objects dwindles, and the background of interstellar particles becomes more noticeable. At each stage, the spacecraft is still, in some sense, within the solar system, though less and less firmly bound to it. This layered structure also means that leaving the solar system takes a very long time. Even travelling at tens of kilometres per second, it takes decades to cross the region of the planets, centuries to traverse the inner reaches of the Oort cloud, and perhaps tens of thousands of years to move beyond its outermost boundaries. When we speak of spacecraft leaving the solar system, we're often referring to crossing the heliopause, because it provides a measurable and meaningful milestone. But in terms of gravity and long-term trajectories, the true boundary lies much farther out, in regions we have not yet explored directly. All of this contributes to the quiet realization that the solar system is far larger than it appears in diagrams or even in most scientific illustrations. It is not a compact cluster of worlds, but a vast sphere of influence, a region shaped by the Sun's gravity and history, extending outward into the depths of interstellar space. And this brings us back to the idea of a one-way journey. The farther you travel from the Sun, the weaker its gravitational pull becomes, but the more energy it would take to return. Distance itself becomes a barrier, not because of any physical obstruction, but because of the time and fuel required to reverse course. Imagine travelling outward for decades, reaching the distant fringes of the heliosphere. Turning around would mean not only accelerating back toward the sun, but also matching the motion of the planets, navigating through the gravitational fields of the outer worlds, and eventually slowing down enough to enter orbit or land. Every step of that return journey would require energy, and energy in space is precious. There's also the matter of navigation. In the inner solar system, spacecraft can use the positions of planets and the sun as references, precise landmarks against which to measure their trajectories. Farther out, those landmarks grow dim and distant. The sun itself becomes just another bright star in the sky, and the planets are invisible without powerful instruments. Navigating across such distances requires extraordinary precision, and even tiny errors can accumulate over years, leading to deviations of millions of kilometers. Correcting those errors requires fuel, which must be carried from the beginning of the mission. Another subtle factor comes into play as well. The farther a spacecraft travels, the more it becomes subject to influences beyond the solar system. The gravitational pull of passing stars, the tidal forces of the galaxy, and the pressure of interstellar gas and dust all begin to shape its motion. These effects are small, but over decades and centuries they can alter trajectories in ways that are difficult to predict perfectly. Returning to the solar system would mean not only reversing direction, but also compensating for all of these influences, matching the changing position and velocity of a system that is itself moving through the galaxy. All of this happens gradually, quietly, without any dramatic moment when the journey becomes irreversible. There is no point at which a spacecraft suddenly finds that return is impossible. Instead, the difficulty increases steadily with distance, until the energy and time required become so great that return is no longer practical. And so leaving the solar system is less like stepping across a threshold, and more like walking into a desert that grows wider and more empty with every step. At first, turning back would be easy. A little farther on, it would be difficult. Farther still, it would be nearly impossible. By the time you reach the farthest edges of the sun's influence, the idea of return has faded into something more like a memory than a plan. Far beyond the orbit of Neptune, past the scattered worlds of the Kuiper belt, there comes a region where the solar system begins to feel less like a structured system of planets and more like a fading memory. The sun is still there, still exerting its pull, but the familiar architecture of orbits and well-known objects gives way to something quieter, more diffuse, and far more mysterious. This distant realm is known as the Oort cloud, and it may be the true outer frontier of the sun's influence. It is difficult to describe the scale of the Oort cloud in ordinary terms, because nothing in everyday life provides a useful comparison. Even the distances between planets, which already seem enormous, are small in comparison. If the orbit of Neptune were the size of a coin placed on a table, the outer edge of the Oort cloud might lie kilometres away. And in between, there would be almost nothing, just darkness, scattered particles, and occasional icy bodies drifting in vast elongated orbits that take millions of years to complete. What makes the Oort cloud especially intriguing is that no one has ever seen it directly. Its existence is inferred from the behaviour of long-period comets, those rare visitors that appear in the inner solar system after journeys lasting tens of thousands or even millions of years. Their paths suggest that they originate from a distant spherical reservoir of icy objects surrounding the solar system in all directions, a halo rather than a disk. This spherical shape is important, because it tells a story about how the Oort cloud likely formed. In the early days of the solar system, when the planets were still taking shape, countless smaller objects were scattered by gravitational encounters with the giant planets, especially Jupiter and Saturn. Many of these objects were flung outward, far beyond the region where planets could form. Their orbits stretched and tilted until they formed a vast, diffuse cloud surrounding the sun. Some of those objects were ejected completely, becoming wanderers between the stars. Others remained bound, moving so slowly and so far away that they have barely changed their positions in billions of years. The Oort cloud, in that sense, is like a fossil record of the solar system's youth, a collection of fragments preserved in deep cold and darkness, carrying with them the chemical signatures of an era long past. Temperatures in this region are unimaginably low, only a few degrees above absolute zero. Sunlight is so faint that it would appear no brighter than a particularly luminous star seen from Earth. Shadows, if they could be cast at all, would be soft and indistinct. Any spacecraft travelling there would experience a sky almost entirely black, with the sun reduced to a bright point among many others. There is a certain stillness in imagining such a place. The icy bodies of the Oort cloud are not rushing about in crowded orbits. They are separated by distances so great that collisions are exceedingly rare. A spacecraft could travel for years without encountering anything larger than a grain of dust. And yet, despite this emptiness, the region is not truly empty. The gravitational influence of the sun still reaches outward, binding these distant objects in slow, delicate orbits. But that grip is weak, and this is where the fragility of the Oort cloud becomes apparent. At such immense distances, the gravity of passing stars begins to matter. A star drifting through the galaxy may pass within a few light years of the sun, close enough to disturb the outer reaches of the Oort cloud. The effect is subtle, but persistent. Over millions of years, these stellar encounters can nudge icy bodies from their orbits, sending some inward toward the sun as comets, and others outward into interstellar space. The galaxy itself exerts tidal forces as well, gentle but unceasing, stretching and reshaping the cloud over vast spans of time. The Oort cloud is not a rigid structure but a shifting frontier, constantly altered by influences far beyond the solar system. This fragility has an important implication for the idea of leaving the solar system. In the inner regions, gravity is strong and predictable, planets follow well-defined paths, and spacecraft can use those paths to navigate and gain speed. In the Oort cloud, gravity is so weak and so easily perturbed that trajectories become more uncertain. A spacecraft travelling there would be moving in a region where small influences, barely noticeable closer to the sun, can gradually alter its course. Another aspect of the Oort cloud that is easy to overlook is the sheer time involved in crossing it. Voyager 1, travelling faster than any previous spacecraft, would require hundreds of years to pass through even the inner portions of the cloud, and tens of thousands of years to reach its outer edge. In human terms, this is not a journey, but an epoch. This immense scale changes how we think about distance and return. A mission lasting decades already pushes the limits of engineering and planning. A mission lasting centuries or millennia belongs to a different category entirely, one in which the original builders and planners are long gone, and the spacecraft becomes more like a drifting artifact than an active vehicle. The farther a spacecraft travels into the Oort cloud, the more difficult communication becomes as well. Signals weaken with distance, spreading out across space and taking longer and longer to reach Earth. Eventually, the delay would become so great that communication would no longer resemble conversation or even correspondence. Messages might take years to arrive, and replies years more to return. At some point, the spacecraft would effectively be alone, moving through darkness without guidance, continuing on a trajectory determined long ago. There is also the matter of energy. Far from the sun, solar panels become useless, and spacecraft must rely on internal power sources that slowly diminish over time. Instruments are turned off, one by one, to conserve energy. Systems go quiet. Eventually, only the most essential functions remain, and then even those fade. In this way, the journey through the Oort cloud becomes not only a physical departure, but also a gradual fading of connection. The spacecraft continues to move, but its voice grows weaker until at last it falls silent. This silence is not dramatic or sudden. It is more like the fading of a distant radio signal, growing softer and softer until it disappears into the background noise of the universe. There is something deeply symbolic about that image. A human-made object carrying the echoes of our civilization, drifting through a region that has remained almost unchanged since the solar system was young, gradually losing its ability to speak, but continuing its journey all the same. And still, even at the outer reaches of the Oort cloud, the spacecraft would not truly be beyond the sun's influence. Gravity would still act, faint but real, shaping its path and binding it, however loosely, to the solar system. Only when it finally drifted beyond that distant frontier, perhaps tens of thousands of years after launch, would it truly become an interstellar object, no longer bound to the sun in any meaningful sense. By then, of course, return would be unthinkable. The distance alone would make it impractical, and the energy required to reverse course would be beyond any foreseeable technology. the spacecraft would have crossed not just a physical boundary, but a threshold of time and scale that separates human journeys from cosmic ones. Reflecting on the Oort cloud also brings a quiet realization about the nature of home. We often think of home as a place defined by proximity, by familiar surroundings and known landmarks. But on the scale of the solar system, home is defined as much by influence as by location. As long as the sun's gravity shapes your path, you're still, in some sense, within its domain. Leaving that domain is not a single step, but a gradual transition. A slow drifting away from warmth, light, and the shared motion of the planets. It is a journey measured not in kilometres or years, but in changes of influence, in the weakening of gravitational ties and the growing dominance of the galaxy beyond. And so, the Oort cloud stands as a kind of threshold, not a wall but a fading boundary, marking the point where the solar system gives way to interstellar space. It is vast, fragile, and almost unimaginably distant, a frontier of frozen time where objects from the dawn of the solar system still drift in darkness. Once a spacecraft drifts beyond the farthest reaches of the sun's influence, beyond the thinning edge of the heliosphere and the distant scattered remnants of the Oort cloud, it enters a region often described in simple terms as empty space. That phrase is understandable because interstellar space contains far less matter than anything we encounter on Earth, or even within the solar system. Yet calling it empty is a little misleading. It is more accurate to say that interstellar space is thin, quiet, and unforgiving. A place where the smallest forces, acting patiently over long periods, begin to matter in ways that are easy to overlook at first. To appreciate this, it helps to imagine the difference between a vacuum chamber in a laboratory and the space between stars. A laboratory vacuum is impressive by human standards, but even the best ones still contain billions of molecules in every cubic centimetre. Interstellar space, by contrast, may contain only a single atom in the same volume, sometimes even less. The emptiness is so profound that a spacecraft travelling through it might go thousands of kilometres without encountering a single particle. And yet, those particles exist. Hydrogen atoms drift through the galaxy, along with traces of helium and heavier elements, forming a diffuse gas known as the interstellar medium. There are also microscopic grains of dust, tiny fragments of carbon or silicates, often no larger than smoke particles. Individually, they are insignificant, but over vast distances and long spans of time, their presence becomes meaningful. A spacecraft moving at tens of kilometres per second carries tremendous kinetic energy relative to these particles. Even a grain of dust striking at such speeds can damage surfaces, erode materials, or create tiny impact craters. Within the solar system, such collisions are relatively rare, and spacecraft are designed to withstand them. But over decades or centuries of travel through interstellar space, the cumulative effect of countless microscopic impacts becomes a quiet but persistent hazard. It is not the kind of danger that announces itself dramatically. There are no sudden explosions or catastrophic events in most cases. Instead, surfaces gradually degrade. Instruments become less reliable. Protective coatings wear away. Tiny cracks form and materials weaken under the combined effects of impacts, radiation, and extreme temperature changes. Radiation, in fact, is one of the defining features of interstellar space. Within the heliosphere, the solar wind and the sun's magnetic field provide a certain degree of shielding from high-energy cosmic rays, particles accelerated by distant supernovae and other energetic events in the galaxy. Once beyond that protective bubble, a spacecraft is exposed to a higher flux of these energetic particles. Cosmic rays are not like ordinary radiation on Earth. They can carry enormous energies, capable of penetrating shielding and altering the atomic structure of materials. Over time, they can damage electronics, degrade insulation, and create subtle changes in the properties of metals and polymers.